Hi everyone, this is Kalyan Kumar here. Welcome back to Chemistry Universe. This is the last video of the electrophilic aromatic substitution, video number 4. In this, we're going to talk about the electrophilic substitution in other types of aromatic rings, both homocyclic and heterocyclic. We'll talk about naphthalene, we'll talk about anthracene, we'll talk about Pyrrole, Furan Thiophene Pyridine, and then we'll do a couple of reactions of alkyl benzenes, which will be helpful for our conversions. And I'll give you a couple of examples of conversions also. So let's get on with the video. This is the electrophilic aromatic substitution in other types of aromatic rings and reactions of alkyl benzene. All right, so here we go. First, let's look at the homocyclic aromatic rings, namely naphthalene is the first. Now, what happens with naphthalene is that naphthalene has two aromatic rings, and therefore one does expect more areneamine structures. So in general, it is known that when you have homocyclic fused aromatic rings, their electrophilic substitution will produce more number of resonating structures for the intermediate, and therefore you will find that they will be more reactive towards EAs than benzene itself. So the delocalization of positive charge is better in naphthalene due to additional resonating structures. Therefore, polycyclic aromatic fused ring systems react faster than benzene towards EAs. Now, the way you number naphthalene, because numbering is important here, because there are different types of positions, you will always, now these are the two bridgeheads, right? Start with the atom attached to the bridgehead, either on the right side or on the left side, either on the top or the bottom, it doesn't matter. That means you can start either with this, or with this, or with this, or with this. So I'm marking this as 1. Now go around the ring, 2, 3, 4, leave the bridgeheads, go to the next ring, 5, 6, 7, 8, in the same direction. Now we don't number the bridgeheads because there are no hydrogens here, even though you can call it 9 and 8, 9 and 10 if you want. But it's not going to make any difference because there will be never a substituent on this because it doesn't have an H. So only H can be replaced, and therefore a substitution can never happen in C9 and C10. So now you will also find that the C1 carbon is similar to C4, C5 and C8. They are all similar. Whereas 2, 3, 6, 7, they are similar. And 1 and 2 are different. So we will basically talk about substitution at 1 and 2 and see where it is more likely to happen. So first let's look at C1. So there is an electrophile here. Pi bond moves to C1, captures the electrophile. You get the first areneamine structure. Resonance takes place. You have another areneamine. Then you have resonance happening again. You get one more structure. And you get totally 5 resonating structures. And as you can see, 5 is anyway better than 3. And therefore, naphthalene on C1 is definitely better than benzene. You'll also notice that if you look at the first two, if you look at this one and this one, I'm going to mark them with a star. This is to tell you that these two are a little bit more stable than others, not perhaps a little bit, a lot stable than the others, because they have one intact benzene ring. And if you remember the Fry's rule that we talked about in GOC, which said that resonating structures with benzene type of rings, benzenoid structures, are more stable because this particular same structure, I can write this with different positions of double bonds. And therefore, that itself will give you additional resonating structure, despite the fact that the plus remains on the same carbon, but the resonating structures are different. So we say that these are aromatic resonating structures. Now, generally, we never invoke resonance in resonance, but in this case, we do because we need to do that. Okay. So these two are more stable than the others. And therefore, the first two structures marked by star are aromatic, and these are called benzenoid structures. Okay. Now let's look at C2 attack. So now the naphthalene's pi bond will move to C2. It will take the electrophile. You get structure number 1. structure number 2. Now this can give you on the right side of the ring structure number 3. And it can give you can make it move on the left side of the ring structure number 4 and structure number 5. Again, you get 5 resonating structures. But do you notice that only the first one is benzenoid? Look at this one. This is the only one which is benzenoid. None of the others are. So I mark this with star. So obviously, as you can see, C1 attack will be better than C2 because there are 2 benzenoid structures in C1 and 1 in C2. So unlike C1 attack, C2 attack there is only 1 benzenoid structure. Therefore, C1 is more likely. And C9, C10 never occurs because there are no hydrogens there. Now, what happens if there are different groups present in benzene? Now, again, just look at the numbering that we had. If I were to show you the numbering again, so this was the numbering of naphthalene. Now, what happens is that if you have an attack, let's say you have a withdrawing group on one of the rings, withdrawing group. Now, withdrawing group will always destabilize, okay? Will not allow electrophilic to happen that easily. So, the substitution never occurs on that ring, it occurs on the other ring, point number 1. Because that itself has a withdrawing group, and withdrawing groups always have minus effects. So, it will happen on the other ring. Second point is, where will it happen on the other ring? It will happen at C5 or C8. If you look at C5 and C8, remember these are similar to C1 and C4. And these are the ones which will give you 2 benzenoid structures. So if there is a withdrawing group, it can be at 1 or 2, it doesn't matter. If there is a withdrawing group on one ring, the substitution will always occur on the other ring at 5 and 8. That is the first point. The second point is that if there is a releasing group on 1, if there is a releasing group on 1, then definitely it will activate that particular ring more. So the substitution will occur in that ring. But where will it occur? Remember, all releasing groups are ortho-para-directing. So if there is a releasing group on 1, substitution can occur at C2 or C4 because that is ortho and para. Now C4 is as it is more likely because of steric hindrance. But other than that, again, C4 has 2 benzenoid structures. So C4 attack is better than a C2 attack if there is a releasing group on 1. Now, what will happen if there is a releasing group on position number 2? Now, if there is a releasing group on position number 2, remember that para of 2 is blocked because that is the bridgehead. No hydrogen, no substitution. So, the only likely places are C3 and C1. They are ortho. And these are ortho-para-directing groups, releasing groups. Out of C1 and C3, which do you think is better? C1. Again, 2 benzenoid structures. So if there is a releasing group in 2, you will find the substitution occurring 1 or 3, and 1 is a little more likely than 3. So moving on, if one of the naphthalene rings has an electron withdrawing group, then the other ring is substituted in positions 5 or 8 as there would be 2 benzenoid structures. Electron releasing groups in position 1 causes the substitution to occur at 2 or 4. Ortho and para to the releasing group. Of these, attack 4 is more likely because 2 benzenoid structures. Electron releasing group in position 2 causes the maximum substitution to occur at 1 rather than in 3, even though both are ortho positions. Again, benzenoid structures. Now let's check up anthracene. Now this is the way you number anthracene. Now you have to start with any one corner ring, and in the corner ring, go to the atom next to the bridgehead. Either this one or this one. So I number this as 1. So go in that same ring with 2, 3, 4. Leave the middle ring. Go to the next ring in the same cycle, in the same direction. 5, 6, 7, 8. Skip the bridgehead. Then go to the middle ring, 9. Then the bottom one, 10. I'm not numbering the bridgeheads as they will not get substituted. So this is the way we number it. As you can notice, C1, C4, C5, C8 are similar. C2, C3, C6, C7 are similar. C9, C10 are similar. So here I'm not going to compare 1 and 2 because we've already done that in naphthalene and we figured out 1 was better. What we will do, however, is compare C1 attack with a C9 attack. Out of C1 and C2, C1 is better. Now we'll compare C1 and C9. So let's look at first the attack at C9. So you have naphthalene here, electrophile, electron moves to C9, attacks, and you get the carbocation, moves here, number 2, and moves here, number 3, and then moves here, number 4. This goes further, number 5. Now, if you go back to this one, I can make the electron go on the right side also. And you get this one. I can make it move it like this. I mean, you can draw all of these on your own also. And you can check whether you're able to draw them or not. Obviously, you can see how many, 7 of them. So it is pretty obvious that naphthalene is much more reactive towards EAS than benzene. Anthracene, in fact, is more reactive than even naphthalene. As I said, more fused aromatic rings that you have, more would be their reactivity towards EAS compared to benzene. All right. So let's look at, now here, as I said, we looked at C1 and C9. We've already seen C9. Let's look at C1 now. Now in C1, as you can see, the electron moves to C1, takes the electrophile, and then keep drawing the resonating structures. And then again, the pi bond moves. And you get this one. Now from here, there are 2 ways. I can make it go on the left side. And further down. And then if you look at this structure again, I can make the electrophile go, the pi bond go, the plus go on the right side. And again, you will notice I got 7 of them. 7 resonating structures. So which one is better? Now let's go back. Let's go back to the C9 attack. In C9 attack, you'll observe that this one has, I mean, if you look at, this one has 1 benzene, 1 benzenoid. This itself has 2 benzene rings. This one has 1 benzene ring. This one has 1 benzene ring. This one has 1 benzene ring. This has 1 benzene ring. This has 1 benzene ring. So every structure here is benzenoid. In fact, in one of them, there are 2 benzenoids in one structure itself. Now, if you were to compare this with the C1 attack, this one has a naphthenoid structure. This thing has a naphthenoid structure. This one has a benzenoid structure, but none of these are. So as you can see, 4 of them don't have any benzenoid structures. 2 of them have naphthenoid structure. 1 has benzenoid structure. This can clearly tell you that C9 attack is better. Moreover, remember the resonance energy of 2 benzenes is more than one naphthalene. That means more number of benzenoid structures is better than more number of naphthenoid structures. So if I have, let's say, a ring having 2 benzenoid and I have a ring having 1 naphthenoid, the 2 benzenoid would be better than 1 naphthenoid because the resonance energy of 2 benzenes is greater than 1 naphthalene. Because in the naphthalene, there is 1 pi bond which is common to both the rings, and therefore its delocalization in either ring is not that much as it would be in 2 independent benzene rings. So that sort of finishes off anthracene. And preferential attack occurs in position 9 or 10 over 1, as in 9 attack, all resonating structures are benzenoid, while in 1 attack, 3 structures are naphthenoid and 1 is benzenoid, while the other 3 are neither. Okay. Rather, it should be the other 4, not just 3. Anyway, so now let's look at the heterocyclic. We'll start with Pyrrole. Now this is Pyrrole. Numbering is done with keeping nitrogen as 1. And then you can go in any direction you want. As you can see, 2 and 3 are unique positions. 2 is similar to 5 and 3 is similar to 4. So let's do C2 and C3 attack. First we do C2. So the pi bond goes to C2, takes the electrophile, and you get the areneamine. And remember, areneamine by default is for aromatic ring, not for just benzene. Now here you will notice there is a lone pair on N, and that makes the octet complete. Now, even though this has only 3 structures, one of the structures has octet complete. It never happened in benzene, it never happened in naphthalene, it never happened in anthracene. They had a lot of structures. None of them octet complete because this is a heterocyclic and there's a lone pair delocalization in the ring. It is automatically bound to have an octet complete structure. So remember, Pyrrole is more reactive than anthracene, which is more reactive than naphthalene, which is more reactive than benzene, because it completes the octet. But remember, we were comparing the C2 and C3. So we just saw C2, let's check out C3. So in C3, you have this, and structure number 1, and there is again octet complete. But can you notice it has only 2 RS? Therefore, C2 tag is slightly more favored than C3, even though both have complete octet structures. But C3 has slightly one less resonance, therefore one less resonating structure, therefore not as much delocalization as perhaps in 2, but there's not much of a difference. So attack at both positions give an octet complete structure. Therefore, Pyrrole is more reactive towards AS than benzene. Position 2 is slightly favored over 3 because of additional structure. Now, if you were to compare Pyrrole with aniline, you will notice that in aniline, the lone pair comes into the benzene ring. It also delocalizes, it also completes the octet. The only difference being that this lone pair delocalization on benzene is disrupting the aromaticity of benzene. Therefore, its ability to delocalize is not that much. Whereas in Pyrrole, the lone pair is very well delocalized because it is this delocalization that makes it aromatic in the first place. That's how it gets 6 pi electrons. And therefore, Pyrrole will be even more reactive. I mean, not only than benzene, it will be more reactive than even aniline. So Pyrrole is more reactive than aniline, as the lone pair of N is better delocalized in the ring due to aromaticity. And if you were to compare furan and thiophene, furan would have less ability to delocalize the lone pair as it is more electronegative. So furan is highly reactive for EAS just like Pyrrole, but it is less reactive than Pyrrole as O is more electronegative and would accommodate the positive charge less readily. In fact, it's not to do with positive charge, it's more to do with the ability to donate its lone pair. Thiophene, in fact, the sulfur one, thiophene, is less reactive than even furan for the simple reason that this lone pair exists in a 3p, whereas the carbon here is only having 2p. So 3p, 2p overlap is not that favored, and therefore this would be not as much as even furan. So thiophene is less than furan. It is less reactive than furan because the overlap of S and C uses orbitals of different energies. Now let's check out pyridine. This is pyridine. We'll start with numbering nitrogen as 1, 2, 3, 4, 5, 6. Now as you notice, 2 and 6 are similar, 3 and 5 are similar, and 4 is unique on its own. So there are 3 attacks that we need to check. Let's start with the C2 attack. So there is an electrophile here. It moves to 2, takes the electrophile, you get areneamine, and here you get this, and you get this. Remember, the nitrogen can never delocalize its lone pair because the lone pair is in the plane of the ring. But can you see here, this is pretty bad structure. You have an octet deficient nitrogen atom with a positive charge. In fact, this will hardly contribute to the actual RS. So which means there are only 2 RS, and both of them are worse than benzene because at least in benzene you don't have minus I. Here you have a minus I of nitrogen, and therefore you will find that pyridine is less reactive than benzene. If I were to look at C3 attack, well, in C3 attack it is slightly better because at least the positive won't come. Remember, the lone pair can't be given here. Remember, whenever there is a pi bond and a lone pair both conjugated, pi bond is the one that resonates for the simple reason that the lone pair is in the plane of the ring. and the positive comes here and the positive goes here. Even though this has more RS, C3 is better than C2 attack, definitely, because nitrogen never becomes divalent, never becomes positive charge. But again, these three are not as good as benzene. And finally, C4 attack. Well, I think this is as bad as the C2 attack, because again, you see nitrogen becoming divalent. So C2 and C4 are bad, C3 is better, but all of them are bad compared to benzene. Less reactive than benzene. All right. So pyridine is less reactive than benzene, as nitrogen is more electronegative than carbon and therefore shows minus I effect. And positions 4 and 2 are less likely, as nitrogen becomes divalent with a positive charge. Now we're going to look at some of the reactions of alkyl benzenes. There are only two of them that we need to look at. One is halogenation, the other is oxidation. The reason I'm giving you this is because this is going to be useful in some conversions that you will do. So we have an R group on benzene, and we're going to check out what reactions can we do with this R, on this R. Okay, we have done the reaction on benzene with an R, but we need to check if we can do any reaction on R if we want. Say, for example, I want to do halogenation. So how do I do that? And you'll notice that R being an alkyl group, its halogenation will follow the same process as that of alkenes, free radical mechanism. Meaning, you can do a free radical halogenation only by using halogen with sunlight or halogen with heat. But in this particular case, since it is the R, the carbon is attached to benzene, it is a benzylic carbon. And if you remember, benzylic and allylic carbons can be halogenated even with NBS, which is what we're going to look at. Okay, so reactions of alkyl benzene, halogenation is the first. And as I said, you can do this with NBS, you can do this with Br2 sunlight, you can do with Br2 heat. You will get Br attached to carbon. And depending on how much bromine you're adding, you can even get all of the hydrogens replaced. And if I were to do the reaction with bromine and sunlight, even in ethyl benzene, it is a benzylic carbon which is going to get halogenated, not the CH3 carbon, because benzylic carbon, the radical is more stable. But if I were to do Br2 FeCl3, remember it's going to attack the ring, para and ortho. Now, sometimes what they would do is, instead of giving you this, they'll simply say Br2 dark, just to show you that you should not halogenate this. Because if they show Br2 sunlight, then it will attack this. Br2 dark, well, obviously FeCl3 may not be given there, but at least we know that if Br2 dark is there, this will definitely not get halogenated. And if they give you options where the only viable option is the bromine in the ring, then you will choose that as the option. So order of stability of free radicals, which we've already done in GOC. Allyl is better than benzyl. Benzyl is better than tertiary. Tertiary secondary, primary. Methyl and vinyl are as bad as can be. Now here, I'm going to give you a particular reaction which has got nothing to do with anything that we have done right now. Nothing to do with EAS, nothing to do with heterocyclic, homocyclic, fused ring, blah, blah, blah. This is something which is going to be useful in conversion. And that is, if you have aniline, that means NH2 sitting on benzene, you can convert this NH2 into NHCOR. Remember, NH2 is strongly activating group. NHCOR is moderately activating group. So I can convert NH2 to NHCOR simply by reacting aniline with an acid chloride, RCOCl. This, of course, we will do when we do amines. Moreover, the amide formed NHCOR can be reconverted to aniline by hydrolysis, acid catalyzed hydrolysis. You can convert NHCOR to NH2. So you can go from NH2 to NHCOR, moderately activating. From moderately activating NHCOR, you can go back to NH2. So this will help you with conversions. So NH2 can be converted to NHCOR by reacting it with RCOCl. NHCOR can be reconverted to NH2 by hydrolysis. Now the other reaction that we can do with alkyl benzene is oxidation. So how do we do that? Any R sitting on benzene with K-4 will become benzoic acid. Doesn't matter how many R's you have. It will form as many benzoic acids. Of course, this is called phthalic acid. Now, this happens irrespective of the alkyl group, how many carbon chain you have, and the number of alkyl groups in benzene. If you have all of them as R, all of them will become COH. But there is one caveat, and that is the benzylic carbon should not be 4 degree. This happens only if the benzylic carbon is not 4 degree. Now, please understand what is 4 degree. It means there is a benzene attached to a carbon. Okay. So this carbon is already attached to one carbon here. If it is attached to 3 more, this is a 4 degree carbon. Now, this is not a 4 degree carbon. This is not a 4 degree carbon. Now, you may say, oh, there are 4 bonds with carbon. Isn't that 4 degree? No. It's not how many bonds it has. It is the number of carbons it is attached to. So, if you have something like this, it is not going to give you any product with KMnO4. You need at least one H on the carbon. Now, you'll also notice one more thing, that if I told you any type of R will do, meaning that if I have this carbon and there is a long chain of carbons, what this reaction is doing is it is breaking this bond, this bond, this bond, but it is not breaking the carbon-benzene bond. Otherwise, you won't get the COH here. So it breaks all other bonds attached to the carbon, but not the benzene-carbon bond. So what would happen is, one important observation is that the only bond that is never broken is the bond between the aromatic ring and carbon. So can you guess what would happen with this? I want you to pause the video, make the product, and then play it back. And here is what you get. I can remember both are equally aromatic, okay? So I take any one of them as aromatic. Now this benzene's carbon and the carbon it is attached to cannot be broken. You can never break this bond, okay? But you can break the benzene itself. That's not a problem. So if one is assumed to be an aromatic ring, I can break the other aromatic ring, but I cannot break its carbon with this benzene ring. So what do you think I'll get? I'll get phthalic acid. If the two COH are ortho to each other, it is phthalic acid. If they are meta, it is isophthalic acid. If they are para, it's called terphthalic acid. Guess what happens with naphthalene, with anthracene? Again, pause the video, make it, try it on your own, and then play the video back. And here is the solution. Now again, remember all the three are equally aromatic. Now, if I were to consider this as one of the aromatic rings, then even this is an aromatic ring, isn't it? Both are equally aromatic, right? But if I were to consider this as aromatic ring, I cannot break this bond, this bond with the carbon. I would have to break this. But if I have to break this, then this is also an aromatic ring. And its bond with this carbon cannot break. So if you were to assume the corner ring to be aromatic, whichever the corner ring you want, the other corner ring will also be aromatic. So you can never break any bond here. So the best is to take the middle carbon as aromatic. I mean, it doesn't matter whether you draw this double bond, you can draw it here also. Consider this is aromatic. Make sure its bond with carbons are not broken. Remember, I can break the aromatic ring itself, but not the bond of the aromatic ring with its carbon. So I can break this, I can break this, I can break this, I can break this. So what do you think I'll get? I'll get this one. Alright, so I'm going to give you a couple of conversion examples. Again, pause the video once the question is given. Try as much as you want and then play the video back. So I want you to convert aniline to first ortho-bromoaniline, meta-bromoaniline, para-bromoaniline, and tri-bromoaniline. You have to start with aniline. You can't start with benzene. You have to start with aniline, go to ortho-bromo, meta-bromo, para-bromo, and tri-bromo. And you can use all the reactions I've told you till now. You don't have to use any other new reaction that I haven't taught you till now. So pause the video, make all of this. Once you're done, play the video back. So here goes the first one. What I do, remember, I can never get monohalogenation in aniline. We've already discussed this. In fact, getting the tri is the easiest part. So if I cannot get mono, what I'll do is I'll convert the NH2 to NHCOR, which is moderately activating, because this will give me mono. But remember, this is ortho-para directing. So if it is ortho-para directing, and the major product will always be para. In fact, we discussed 90% is para. But I want the bromine at ortho. So I'll temporarily block the para with sulphonation. Now my ortho is the only place where it can attack. And coincidentally, this also happens to be the meta of SO3H, in which this is the meta directing group. So it is both ortho to this and meta to this. So the both reinforce each other. So the only place bromine can go is the ortho. And now I do hydrolysis. Now the advantage of doing hydrolysis is when you do hydrolysis, you also have to heat it. So not only will it convert this back to aniline, the NH2, it will remove this also, because remember I told you in desulfonation, all you do is add steam to it, and which is what we are adding here. And therefore you get ortho-bromo-aniline, and the SO3H also goes away. Now let's make the meta. Meta is perhaps the easiest apart from the tri-substitution, because all I have to do is do Br2 FeBr3. Remember, FeBr3 is a Lewis acid, and the Lewis acid will react with NH2, will form a coordinate bond. It will convert the N into a plus. Its lone pair will be gone. It will become a strongly deactivating group, and a strongly deactivating group always orients meta. So I'll get this. And if I want to remove FeBr3, all I do is hydrolysis. I remove the FeBr3 and you get back NH2. Let's make para. By now, I think you would have understood how to make the para. So all I do is again convert this into NHCOR. But now I don't need sulphonation because I need the para at I need the bromine at the para. So I do Br2, water. That is what we use for halogenation of moderately activating groups. Para-bromo, hydrolysis, and I'll get NH2. And tri-bromo is the easiest. We've already done this. All you have to do is halogenation in CS2 and you'll get tri-bromo. The second conversion I want you to do is this one. Convert benzene to this. Now, before you start, let me just point out one thing. Don't think of this as a para position. Generally students believe, oh, this is para. There's nothing called ortho-para in a benzene, number one. They are always relative. Now, this is para only if there is a group here. But here the group is here. So it is actually meta. 1,3 is meta. Remember, 1,2 is ortho, 1,3 is meta, 1,4 is para. So this is actually NO2 and CH2 sitting on para position, the meta position to each other. So I want you to pause the video and make the conversion happen. And so let's start the solution. Now, one thing that I've always noticed with my students, and this is very natural for it to happen, is that they'll say, okay, I'll do halogenation, I'll do alkylation, and then I'll do nitration. But if you do alkylation first and then do nitration, nitro will go to ortho or para. But I want it in meta. So the moment I point this out, they'll say, okay, first let's do nitration and then do alkylation because nitro is meta directing. But remember, I've already told you that when you have a strongly activating or a strongly deactivating group on benzene, you can never do Friedel-Crafts alkylation or acylation. So you cannot do nitration first and then do alkylation. So this is where students get stuck. So here is one of the solutions. There are many solutions possible. I'm pointing out one of them. And it need not be the best possible solution also, because best would be the ones in which you get better yield and lesser number of steps. So I'm not taking that into account right now. I just want to convert it into this, and I'm going to make sure every step I get the major product. All right. So I take benzene. This is where we have to start with. I do alkylation. Now you'll say, okay, you said we should not do alkylation first. I never said that. I said you can't do nitration right now because it will go to para or ortho. Instead, what I do, a reaction that I just told you now, K1O4. Benzoic acid, isn't it? Now, what is the orientation of COH group? Meta directing. So now I do nitration and I get meta. Remember when we did acylation, I gave you a lot of complicated reactions there. And one of the reactions we used was benzene PPA. What do you think benzene PPA did? PPA removed the OH and attached benzene. That's what happens. Now what happens when I do Clemenson's reduction? It'll convert the ketone into a hydrocarbon, won't touch the nitro at all, and you get the product. And that is the end of this particular video. So I hope this video helped you in understanding the other types of aromatic rings and perhaps helps you with conversions. So you can download the PDF of this if you were to visit chemistryuniverse.com. And there you can download all PDFs of all the videos that I've made so far. I'll be uploading all these videos in a couple of days. And once that is done, you can check out the chemistryuniverse.com. You have to first sign up, then log in. And in courses, you go to J class 11th. And in that, you go to organic chemistry. And then you will find the list of topics and hit the topic that you want. If it's videos available, you will see it there. And if the video is available, there will be a button that says download PDF. You can hit that and download the PDF there. So with that, we come to the end of this video. I hope you understood whatever was presented to you. Watch it as many times as you want. And thank you for watching this.